welcome to Physics Online Classes by Yusuf Arikewuyo. Today we shall be looking at the concept of dimensional analysis. When we talk of dimensional analysis, we are simply looking at the situation whereby we obtain equivalence between the formula and the concept or the quantities used in its calculation. There are so many ways to go about dimensional analysis, but we shall make use of the MLT system in today's video, whereby the M stands for mass, the L stands for length, and of course the T stands for time. Usually, the dimensional analysis considers the concept of basic and fundamental, or basic, otherwise called fundamental quantities, as well as the derived quantities. When we talk of basic quantities, they are quantities that are naturally occurring, and they are grouped into 7. They include mass, length, time, current, amount of substance, luminous intensity, you have temperature, all right. Away from the basic quantities are the derived quantities, and they are quantities that are not found in the basic quantities. Some include velocity, acceleration, you have force, momentum, impulse, and so on and so forth. So today's example, we shall be looking at how to generate the dimensional analysis for some of these derived quantities. Let me take a new screen. All right. For example, if we are told to get the dimension for velocity, the first question we ask ourselves is, what is the definition for velocity? Velocity is simply defined as displacement per time, right? By definition, we say velocity is the rate of change of displacement, or simply say velocity is a change in displacement with time. Then we ask ourselves, is displacement a basic quantity or a derived quantity? Of course, the SI unit for displacement is meter, which is the same as that of length, and length is a basic quantity since it goes in line with the MLT system, with L representing length. And of course, we are going to say velocity, velocity will be equal to displacement, now will be represented with letter L, divided by time, which is capital letter T. And of course, the dimension of velocity will be LT raised to power minus 1. Alright, let me change the slide. We can be told to find the dimension for acceleration. All we need to do is to define acceleration, and by definition we define acceleration as the rate of change of velocity, which is velocity over time. Already we know the dimension of a velocity as LT raised to power minus 1, and that of time as capital letter T. Then by law of indices, we know this becomes LT raised to power minus 2. Alright, that is, what we did here is to say LT raised to the power minus 1 times 1 over t, which is LT raised to the power minus 1 times t raised to the power minus 1. Sorry about that. It's actually the edge of the board, minus 1. Let me change the slide. So we now have LT raised to the power minus 1 plus minus 1, which of course will give LT raised to the power minus 2, and that is the dimension for acceleration. Acceleration equals LT raised to the power minus 2. Let's quickly try this. Get the dimension for force. The dimension for force. Note that the formula for force equals mass times acceleration. And of course we know mass. Sorry about that. Let me take this out. Okay. Alright, we know force is mass times acceleration, and we know that force will be given as capital letter M times LT raised to the power minus 2, which gives, let's take a new slide, it gives F equals M LT raised to the power minus 2. Alright, thanks for watching. We shall meet in the next